Hello, welcome to this lecture. We're going to continue Chapter 8 from where we left off in class on Monday. A couple of announcements. The Chapter 8 Part 1 Achieve will be due on Tuesday, so that's November 28th that will be due. And then this lecture, this is a lecture that you should finish watching before our class on Monday, November 27th. You might watch this lecture in segments instead of watching the whole thing at once. That might help you digest the information a little bit better. It's totally up to you though. So let's continue. We ended class working through a problem here. So just before this, we had learned this equation to describe the energy that is lost or gained by an atom when an electron absorbs energy and jumps to a higher energy state, or releases energy and relaxes back down to a lower energy state. This is also equal to the energy of the photon that is absorbed or released. So an atom must absorb a photon for an electron to increase in energy level. If an electron decreases in energy level, then it releases a photon. So we calculated in class the energy change in an atom when the electron changes from the fourth energy state to the second. So it was initially at the fourth energy state and it relaxed back down to the second. This means that a photon was released. So the change in energy of the atom, so this describes the atom that holds that electron. The energy change is negative because it had released energy, so we use that equation to calculate it. Now we're also asked, what is the wavelength? So remember, wavelength is lambda. What's the wavelength of the photon that is emitted? Well, the energy that is lost by this atom, in this case, is equal to the energy of the photon that was released by the atom when the electron relaxed back down to a ground state. So that means that the energy of the photon is equal to positive 4.088 times 10 to the negative 19 joules. But we are looking for wavelength. So our equation that involves wavelength, I'm going to write these over in the right corner. We have the speed of light is equal to wavelength times frequency. But we don't have frequency yet, so we can't use this equation at the moment. But we also have this equation that energy is equal to Planck's constant times frequency. So we can rearrange where energy divided by Planck's constant is equal to frequency and plug this into this equation up here. So we have speed of light is equal to wavelength times energy divided by Planck's constant. Now we're looking for wavelength, so let's rearrange. We multiply by Planck's constant divided by energy on both sides. So now we have Planck's constant times the speed of light divided by energy is equal to wavelength. And we have our two constants and we have energy. So we can go ahead and plug that in. Just to rewrite that equation, lambda equals Planck's constant times speed of light divided by the energy. Planck's constant is 6.626. Again, this is provided for you on the periodic table equation sheet. Times 10 to the negative 34th joules times second. Speed of light is 3.00 times 10 to the 8th meters per second. And then the energy we just calculated, 4.088 times 10 to the negative 19 joules. So in this equation, we cancel out joule units. It's in the numerator and the denominator. And then we have seconds and seconds to the negative first power in the numerator, so those are canceled out as well. We're left with just meters as our unit, and that's good because we're looking for wavelength, and wavelength should be a unit of length. So if you simplify this whole fraction, we have that the wavelength is equal to 4.86 times 10 to the negative 7th meters. So there is the wavelength of the photon that is emitted. Okay, so we've mentioned that electrons can excite to very specific energy levels and can relax to specific energy levels. So here are some diagrams that show that. If we think about a ball on a staircase, so there are given steps where the ball can fall or be carried up to. It's kind of similar to what happens with an electron. So a ball would not be able to exist anywhere between these two steps because it would just fall to the lower step. It's the same thing with an electron. Here's an energy level diagram. So in the center here now, an electron, or if you're increasing energy, this can increase into, let's just say, the highest energy level that's represented here. So now we're up at the top of the diagram. If something loses energy, then its change in energy is equal to the energy state after it had lost energy minus its initial energy state. Now, if we look at this third diagram here, this is more specific to an electron. If it starts at a low energy state, so down here, and absorbs energy from a photon, then it can increase, depending on the energy of the photon, can increase to a higher energy state. This diagram shows it increasing all the way up to the 5th energy state, but it's possible for it to end at the 2nd or end at the 3rd. And then as the electron relaxes back down, it emits energy in the form of a photon. So this is all summarized in text on this slide. So electrons cannot exist between energy levels, only on specific energy levels. As a photon is absorbed, an electron is excited to a higher energy level. So the energy of the photon is equal to the energy change of the electron or the atom that is holding that electron. And then as an electron falls back down to a lower energy state, a photon is emitted, and the energy of that photon emitted is the same as the energy change for the falling electron. And the specific energy of the emitted photon dictates the color. So in other words, the wavelength. This next slide shows all of the energy levels possible for a hydrogen and hydrogen atom. So an electron starting at the lower energy state, the first arrow shows it is getting excited to the 6th energy state. The second arrow ends at the 5th, and then the 4th, the 3rd, and the 2nd. If an electron is starting at the 6th energy level and relaxes all the way back down to the 1st, that emits energy in the ultraviolet range. So you can follow the arrow, follow the arrow that shows where that wavelength would be for that emitted photon when that electron relaxes back down to ground state. So all the way from an excited state, any excited state, to the lowest energy level releases ultraviolet light. Now, if we start at an excited energy state, again, let's say we're starting at 6. Maybe I'll use a highlighter. So we're starting at 6 and going back down to level 2. So we're not going all the way back down to level 1. That emits energy in the purple visible light color, so about 410 nanometer wavelength. If we start at the 5th energy level, we relax back down to the 2nd. That emits light in the blue visible light range. And then we can follow the rest of these arrows to see where the different energy changes are appearing on an emission spectrum. So this is the emission spectrum for hydrogen. Oops. One more thing, if the electron starts at the 6th, 5th, or 4th energy level and relaxes back down to the 3rd, all of these correspond to infrared emission. So hydrogen has 4 emissions that are in the visible light range, a few in the infrared, and a few in ultraviolet. If we then go and look at mercury, so notice these are a bit different. This is because we have a different atom, so all different atoms have unique emission spectra. The absorption spectrum shows 2 dominant lines. These are the upward arrows. And then the emission spectrum contains many different wavelengths, and these are all the downward arrows. So upward arrows are this red arrow, and then these blue arrows over here. Oops, the blue arrows. Depending on where the electron is starting off in its energy state and where it's relaxing back down, we again have different wavelengths of light. So we have some showing ultraviolet light and then some showing visible light. But again, this looks different than the emission spectrum for hydrogen because we're working with a different element. Okay, a little bit more about this wave-particle duality of matter. So how we can describe matter as a wave and we can describe it as a particle. Now, we're really focused on electrons in this chapter. And each electron has the same mass and the same charge. We learned about this in an earlier chapter. We have the mass of an electron and the charge of an electron in units of coulombs. Electrons also have magnetic properties. So some types of atoms behave like magnets, where they can be attracted or affected by a magnetic field. And this magnetic behavior is caused by magnetic properties of their component parts, specifically the electrons. So magnetic properties of electrons arise from a property called spin, and an electron spin can respond to a magnet in different ways. So we have electrons that have mass, so they are a particle with mass. They have a charge, and they can respond to magnetism. A French physicist suggested this wave property of an electron. So electrons display wave particle duality that is also exhibited by photons. And so the de Broglie equation links the wavelength of a particular particle with its mass and its speed. Okay, I'll reiterate this. So an electron has mass. We've shown the value of the mass of the electron, but it also moves through space in a wave pattern. And so electrons, just like photons, display this wave-particle duality where we can describe its wavelength because it has properties of a wave, and we can describe its mass because it has properties of a particle. So this equation here relates the wavelength of the particle. This is Planck's constant. This is the mass. And this is the speed. Here's a summary slide. So both photons and electrons, we say, are particle waves. So they have properties of a particle, they have properties of waves. So each are described with different equations. So for the energy, for looking at energy of a photon, energy is Planck's constant times frequency. The energy of an electron is mass times speed squared divided by 2. And then I won't go through all of these equations, but we can see that the equation for a wavelength of a photon is slightly different than the wavelength of an electron. The speed of a photon is slightly different from the speed of an electron. The speed of an electron depends on its kinetic energy. So kinetic energy equation is up here. All right, so we can describe, again, electrons as a particle with mass and a wave. This uncertainty principle, Heisenberg's uncertainty principle, states that the momentum, so related to the electron's speed, and the position of the electron cannot be simultaneously known. So we cannot calculate the position and the momentum of an electron at one moment in time. So this is because a particle will occupy a particular location, but a wave has no exact position. So any wave, something that is a wave, like an electron, extends over some region of space. So electrons are always spread out rather than located in one particular space. So the position of a moving electron cannot be precisely known. And electrons are described as delocalized. You'll hear this word a lot in organic chemistry. So they're described as delocalized because their waves are spread out rather than pinpointed. We're going to talk about in the next section what these areas look like where an electron can exist in an atom, but we cannot know exactly where an electron is. We just have an idea of a space, an area where the electron can exist, but the specific location is unknown. And that brings us to our next section. So orbitals and quantum numbers is section 8.4, and then orbital shapes is section 8.5. These are really similar. They go hand in hand, so we're going to cover them together in this section. So if we're thinking about a bound electron or a free electron, some properties are different. So the properties of mass, charge, spin, and wave nature apply to all electrons, free or bound electrons. Bound meaning it's orbiting in a nucleus. Of an atom. Free electrons not orbiting a nucleus. So the energies of bound electrons, so an electron that is part of an atom, are quantized. And we talked about that in previous sections. Can only exist, energies of bound electrons can only exist at specific energy levels. That's what we mean by quantized. So bound electrons have additional properties related to their shapes of their waves. So a 3D wave can be illustrated to describe the spatial distribution of an electron around a nucleus. And these 3D waves are called orbitals. So an orbital is a three-dimensional volume. You can think of maybe a balloon. So a balloon has a three-dimensional volume. If a balloon is tied to a nucleus, imagine inside of the balloon, that is where an electron can exist. But we don't know exactly where within that balloon that the electron is existing. So if we have a nucleus and one of the orbitals that we'll talk about has a shape like this, kind of similar to a balloon. There are actually two, top and bottom. An electron can exist somewhere in these orbitals, but we, again, don't know exactly where. So it's a three-dimensional volume, and the shape of a particular orbital shows how an atomic or molecular electron fills three-dimensional space. So an atomic electron, if you're just looking at an individual atom, an electron on that atom, we can describe as an atomic electron. If you're looking at a molecule like water, their orbitals look a little bit different in a water molecule, but again, in a orbital is in a molecule is a three-dimensional space that an electron in that molecule can exist. So just like energy of electrons are quantized, so they can only exist at specific energy levels, orbitals also have specific shapes and orientations. A little bit more about orbitals in this next slide. So just to repeat the last slide, they are a 3D space around a nucleus where an electron can be found. The shape of an orbital represents the electron density around a nucleus, and each orbital can hold a maximum of 2 electrons. So we have a 3D space that can, the amount of space of an orbital can occupy, or more than 2 electrons would be able to fit inside that space. But because of electron repulsion, only 2 would be within each orbital. We're going to talk first about quantum numbers, and these quantum numbers give us information about the size and the shape of the orbital that specific electrons can occupy. So after talking about quantum numbers a little bit, we'll start talking about shapes of these orbitals. So quantum numbers are used to identify quantized properties, and really these are, again, focused on electrons. So we have 4 quantum numbers. Each will tell us a little bit different information. So first is represented by the letter N. So N is the principal quantum number. And this describes orbital energy and indicates roughly how far an electron is away from the nucleus. So all orbitals with the same principal quantum number are in the same shell. When we were looking at energy diagrams, let me go back to this slide. Like for this energy diagram for the hydrogen atom, notice that the y-axis is letter N. So all of these are principal quantum numbers. So generally, if you have the same orbitals with the same principal quantum number, are the same energy. All right, let's go back down to our slide. L is, so lowercase l is the secondary or azimuthal quantum number. This describes the energy and shape of an orbital. So all orbitals with the same secondary quantum number are in the same subshell. So we'll talk about shells, we'll talk about subshells. M, letter M with the lowercase l subscript, is the magnetic quantum number. This describes the orientation of an orbital. Hopefully this will make more sense as we talk about specific orbitals. And then M with a lowercase f is the spin quantum number. And this describes the spin of an electron. Okay, let's talk a little bit more about each type. So the principal quantum number, this indicates the energy of an electron in an atom. N must be a positive integer. And the lower the value of n, the lower the energy, and thus the higher the stability of an electron. So a lower n value means it's closer to the nucleus, and that's what these diagrams are showing. So here, n is equal to 1. An electron is somewhere orbiting the nucleus about this far away. And so this is a lower energy electron. Lower n value means the orbital is smaller. If we look at where n equals 2, the electron is further away from the nucleus. Higher principal quantum number means higher energy and further away from the nucleus. So the higher the value of n, the more the orbital is spread out in space, and the higher the energy of the electron and the lower the stability. So if you have a low principal quantum number, the electron is held tightly to near the center of the nucleus. If you have a large quantum number, we can go even up to 6, that electron can occupy a larger space around the nucleus, and so it has a higher energy as it's orbiting the nucleus. The secondary or azimuthal quantum number describes the shape of the atomic orbitals. This is L, so lowercase l, along with N, describes the energy of an electron in an atom. Make all of those L's, they kind of look like I's, but they are all L's. Okay, so this describes energy, and L is designated with numbers or letters. So we will often say that the value for L is 1, 2, 3, 4, 5. But if we have a value of 0, this means that the type of orbital is an s orbital. And s orbitals have unique shapes from p orbitals, d orbitals, and so on. So if L is valued at 1, then that orbital, that number, is describing a p orbital. If L is 2, describes a d, and so on. If L is 5, describes an h orbital. So each number or letter for L indicates the shape. And as L increases, the shapes of these orbitals become more elaborate. So we'll see s and p orbitals are quite simple, and then d orbitals are a little bit less simple and more, and so on as we go through F, G, and H. And then L can have integer values from 0 to n minus 1. So this means that n, the principal quantum number, is always greater than L. So for example, if we have n is equal to 1, we have an electron in the first energy level, then L can only equal 0. It can't equal 1, it can't equal 2, 3, or 4. It has to be less than n. But if we have a principal number, n equals, let's say, 4, then L can equal 0, 1, 2, or 3 for that atom. We'll talk a little bit more about possible sets of quantum numbers in a little bit. So let's look at these shapes. We're just going to talk about s, p, and d orbitals. So if L, lowercase l, secondary quantum number is equal to 0, this orbital is an s orbital, and s orbitals have a spherical shape. For each s subshell, there's only one orbital. So if you are talking about an s orbital for an atom, there is only one possible orbital at each principal quantum number, at each energy level. For when secondary quantum numbers equal 1, that indicates that we have a p orbital. P orbitals have two-lobed shape. So if we look all the way to the right, we have in this case, along the x-axis, one p orbital kind of looks like a dumbbell. P orbitals, if your electron occupies a p orbital, there are 3 orbitals per each subshell. Well, we have another slide to look at all 3 of these p orbitals. And then d orbitals are when L is equal to 2. So the d orbitals have a 4-leaf clover shape. So one of the 5 d orbitals is shown here. Or a 2-lobe shape like a p orbital with a ring. So here's an example of how, as we increase in secondary quantum number, the orbital shapes get a little bit more complex. And then for each d subshell, there are 5 orbitals. For any orbital, if we're even just talking about s orbitals, if n has increased, then the size of the orbital has increased. So an s orbital at principal quantum number 1 is smaller than an s orbital with principal quantum number 4, for example. And that is displayed on this next slide. So here are some s orbitals. And remember, they have a spherical shape around the nucleus. So a nucleus, remember, has a positive charge. That would be right in the center. So you can think of an s orbital kind of like a basketball. Imagine a nucleus in the very, very center of the basketball. Then an electron can occupy the space around the nucleus in a spherical shape. So it won't go outside of that sphere. These numbers and letters here indicate the number here is n, so principal quantum number. Principal Q number. And then S is shape, so that's L, the secondary quantum number. So if principal quantum number is 1 and L, secondary quantum number, is 0, then we have this 1s shape. If principal quantum number is 2, so here we have n is equal to 2, then the L can equal 0 or 1. This is principal quantum number 2 with L still equal to 0. If L equals 1, we have the p orbital shape. And then for our largest orbital here, n is equal to 3 and L is still equal to 0. So this is displaying that as the n value, principal quantum number, increases, then the size of this orbital, or the amount of space that an electron can occupy, also increases. And again, s orbitals, there's only one orbital at each principal quantum number. And that's different when we're talking about p orbitals. So p orbitals have a 2-lobe shape. These 3 diagrams here show the 3 p orbitals. So we said 2 slides back that there are 3 orbitals within a p subshell. So a p orbital is one of the 3 lobes that make up a p subshell. These again increase in size as the value of n increases. So if we have L is equal to 1, we're looking at p orbitals. If we say this is, remember, L can only equal up to n minus 1. So if this is n equals 2 and L equals 1, to describe these 3 orbitals here, then if we're looking at n equals 3 and L equals 1, we have the same shape, just larger size. So same shape if L is always equal to 1, but different sizes. And this last image here shows if all of these lobes are overlapping, what that looks like. But we discuss often p orbitals as the individual orbitals, and we describe them as px, py, and pz, and that just indicates which direction of the 3D space x, y, and z the orbital occupies. All right, and then we have d orbitals, and this will be the most complicated that we talk about. These have a more complicated shape. We have 5 d orbitals that make up each d subshell. These again increase in size as the value of n increases, and this is when our secondary quantum number equals 2. We have a d, we're talking about a d orbital. So this shows the 5 different individual p orbitals that exist if you have an electron with a principal quantum number 2. 4 of them are the 4-leaf clover shape in different 3D space. And then one of them, this last one, is the dumbbell with a ring, or it kind of looks like a donut around the center. Okay, so principal quantum number n tells us energy level and size. Principal quantum, or not principal, but secondary quantum number, which is L, tells us the shape of the orbital, but we know that p orbitals and d orbitals can exist in different orientations. So the next quantum number, the magnetic quantum number, describes the orientation of the orbital. So the values for m with a subscript lowercase l range from negative L, so whatever value that L value is, to positive L. So here's an example of a football that doesn't exactly align with an orbital per se. But this football, if you have a football, imagine that's our orbital. Well, it could exist around the nucleus along the y-axis, along the z-axis, along the x-axis, or in between the x and y. So these are different subshells of a football orbital, and whatever value the magnetic quantum number is would indicate the orientation of that orbital. Now, s orbitals, like a basketball, so remember an s orbital is a spherical shape. They can only be oriented one way. If you kind of rotate it around, it's still a sphere. But if we have a football, like a p orbital, that can be oriented in a number of different ways, and that's why we have this magnetic quantum number. So a p orbital can be oriented across a set of 3D axes 3 different ways. Remember, a p orbital, L equals 1. So if we think about what ml can equal, this can equal negative L to positive L. So it could equal -1, 0, or 1. So there are 3 possible numbers for ml, when L is equal to 1, there are 3 different orbitals for p orbitals. So you could have the orbital along the x-axis in 3D space, along the y-axis, and along the z-axis. If we look at d orbitals can be oriented across a set of 3D axes 5 different ways. So d orbitals, L is equal to 2, ML is equal to -2, -1, 0, 1, or 2. So negative L to positive L, that's 5 different values. We have 5 different orientations for d orbitals. And those are all shown on this slide here. To summarize, each subshell contains a specific number of orbitals. So an S shell contains 1 s orbital. So anytime you're talking about an s orbital, there's only 1 that's present there. A p subshell can contains 3 p orbitals. So here's an s orbital, here's p orbitals, there are 3. A d subshell contains 5. And an F subshell, which we haven't talked about in detail, but that's okay. But these contain 7. So you'll notice that the orbital increases by 2 in each case, but we're sticking with odd numbers. So 1 s orbital, 3p, 5d, or 7f. Here's another summary slide here. We're also aligning with principal quantum number. So if principal quantum number is equal to 1, then we have 1 s shell where L is equal to 0. Remember, L must be equal to n minus 1. So if principal quantum number is 1, then only the s orbital can exist. The p orbital cannot, because this is where L is equal to 1. D orbital, L is equal to 2, and F orbital, L is equal to 3. So if we have only an s shell, we have 1 orbital, and that means only 2 electrons can occupy that orbital. 2 electrons can occupy each orbital maximum. If n is equal to 2, then L can equal 0, and L can equal 1. So that means if we have principal quantum number 2, then we can have an s orbital and a p orbital. Principal quantum number is 3, we can have an s orbital, a p orbital, and a d orbital. Quantum number, or principal energy level, principal quantum number is 4, we can have an s, p, d, or f, and then at higher energy levels we can have the g and h orbitals. So we said that, for example, in the d subshell, there are 5 orbitals in different orientations. Since each orbital can hold 2 electrons, then in the d subshell, there can be 10 electrons held there. All right, our last quantum number is the spin quantum number, and this is m with the subscript s. So spin quantum number describes the magnetic properties of electrons. So atomic electrons interact with a magnetic field in one of 2 ways. They can have a clockwise spin, or we say this is spin down, or a counterclockwise spin, and we say this is spin up. So they're represented here. We have an electron spin up. It interacts with a field clockwise, and then spin down counterclockwise. So for an electron, the spin quantum number m subscript s can have only one of these 2 values. So it can be plus 1/2, and that would be spin up, or it could be minus 1/2, and that could be spin down. There will never be other values for a spin quantum number. Let's summarize these restrictions, because we've talked about a lot of restrictions on these quantum numbers. if we have a complete set of quantum numbers, so N, L, ML, and MS, that describes an individual electron. But those 4 numbers must meet all of the restrictions that are summarized below. So for one, our principal quantum number N must be a positive integer. So it cannot be 0, it can be 1, 2, 3, 4, 5, 6, etc. It can't be 1.5, can't be -1, only positive integers. Once you set quantum number N, this sets L, the possible numbers for L, and the possible numbers for ML. So remember, L is our secondary quantum number. L is also positive integers, but they have to be less than N. So if N is 1, then the only value for L that can exist is 0. If N is 2, then L can be 0 or 1. Both are possible with an N is equal to 2. And so on until you get to N minus 1. L can never equal N. It has to be lower, but it can equal 0. ML can only be integers between positive L and negative L. So let's say L is 2, then you can have -2 as an ML value. You can have -1, you can have 0, you can have +1, you can have +2. So it can never be greater than N or less than -N. And then for MS, the spin quantum number, they are always half integers, plus 1/2 or minus 1/2. And the key here, remember that each orbital can only hold 2 electrons? Well, the 2 electrons in that orbital must have different spins. So if you're talking about the 2 electrons in an s orbital, one has spin up and one has spin down. Any set of quantum numbers that doesn't obey these rules is invalid. It doesn't correspond to an orbital, it cannot be used to describe an electron. So let's do one learning check to finish off this lecture here. That is to provide 2 examples of sets of quantum numbers for 4D orbitals. So you're describing 2 electrons that can exist in a 4D orbital. You might pause the video here, try working through this on your own. Maybe if you can only find the principal and secondary quantum number, that's fine, at least you're getting started. If we were in person, I would give you all time to work on this. Since I am recording this, I will go through it now, but again, I encourage you to pause and try working through this. So we are providing 2 examples of quantum numbers for 4D orbitals. Well, we already have information here that we can work with. The 4 in 4D, this tells us our principal quantum number. And D indicates what our secondary quantum number is. So our principal quantum number N is equal to 4. Our secondary quantum number, we have to remember what the d orbital secondary quantum number is. Well, L can equal 0, 1, 2, 3, 4, and so on. 0 corresponds to an s orbital, always, and L of 1 corresponds to a p orbital, and an L of 2 corresponds to a d. 3 is F, and so on. So if we have a 4D orbital, that means that our L value is 2. Now, ML can equal -2, -1, 0, +1, +2. So we're providing two examples. We don't have any information about what the ml value is, so you could pick any number here between -2 and +2. So I'll pick -1. Why not? And then the ms, the spin, can equal +1/2 or -1/2. So I'll just pick positive. So that's one example. To provide a second, n must also equal 4 because we're in the 4 energy level. Principal quantum number is 4. L also must equal 2 because we are told that it's a d orbital, and that's described with an L is equal to 2. ML, again, can equal any number between -2 and +2. To demonstrate MS, I'll stick with -1 here, but again, you could pick different values. Now, 2 electrons cannot occupy the exact same quantum number, or the exact same set of quantum numbers. So far, the 2 sets that I've shown are equivalent except for this last value. So this ms value, if I'm going to show a different quantum set, this will be equal to -1/2. So 2 electrons in the same atom cannot have the same set of 4 quantum numbers. So 4 quantum numbers, meaning we have a number for n, l, ml, and ms. If you're describing 2 different electrons, then they must at least differ by the ms value. All right, 2 more quick slides here, and then we will finish off this section of notes, and we'll be done for the video. So as an orbital gets larger, the value of n, of course, is increasing. And this means that the distance from the nucleus of an electron in that orbital is also increasing. So we're increasing, going left to right. This plot shows all s orbitals. So the 1s orbital is this orange color, 2s is blue, 3s is red. The 1s orbital, electrons in that orbital can exist up to this distance from the nucleus. 2s orbitals can exist up to this distance, and 3s can exist up to this distance. So if you have this nucleus in the center, 1s, say this hand represents distance from the nucleus, 1s would be really close to the nucleus, 2s would be a little bit further away, and 3s is even further. As you increase in principal quantum number, you get further and further away. So the number of nodes, this is a new word here, the number of nodes increases as n increases. This is a place where electron density is 0. In the 1s shell, there are no nodes. The only place where electron density is 0 is right here, and this is where distance from the nucleus is 0, so this is where the nucleus would exist. And no electrons are there, because that nucleus is just protons and neutrons. If we look at the 2s plot, use a laser pointer. So this blue line here that I'm tracing, there is a little bit of possibility that an electron can exist this space close to the nucleus, and then the possibility of electron density is 0 right here. So this is a node. So a node where electron density is equal to 0. Now this node only exists in the 2s and the 3s orbital. This is not a node for the 1s orbital. And then the 2s orbital can have a distance up to here. These are all relative values, of course, of where the electron can exist, and there's just one node for that orbital. Now for the 3s orbital, there's a node here, and there's another node right here where no electrons can exist, and then electrons can occupy a distance from here. So as n increases, so we go from 1s to 2s to 3s, the number of nodes increases. Now these are for 1s, 2s, and 3s orbitals, so all s orbitals. Now if we look at orbitals with the same n, so same principal quantum number, they are similar in size. So these all show principal quantum number 3. We have the 3s orbital, the 3p orbital, and the 3d orbital. So the 3 orbitals are nearly the same in size. So they occupy almost the same distance from the nucleus. Again, all with the same n value. The difference is in their shape, but if we're talking about just distance from the nucleus to the edge of the orbital, that's about the same for the 3s shell, the 3p, and the 3d shell. All right, that will end this section. So we'll be done for the recording, and I will see you all in class on Monday.